Hello, my name is Kira Patel, and today I'll be presenting my Physics 2212 Lab 2 magnetic field of a bar magnet. I'll first go through the introduction, then the purpose, important concepts, the observed model, the computational model, results, uncertainties, and finally, relevant questions. In this experiment, I explored the magnetic field of a bar magnet and how it varies with distance. I used a magnetometer app on my smartphone to measure magnetic field components at various distances. My goal was to determine how the magnetic field's magnitude depends on distance and to compare measurements to theoretical predictions from Biot-Savart law. My key findings were use of mag equals 3.3614, and the experimental magnetic field was 4.02352 times 10 to the negative 5, and the computational magnetic field, on the other hand, was 4.358 times 10 to the negative 5. Later in this presentation, I'll explain why this discrepancy was caused. To experimentally describe the exponent n in this relationship and the equation shown on the right for a bar magnet was the purpose of this lab experiment. It was also to compare on-axis and off-axis field measurements with calculated predictions using VPython, and to visualize the dipole magnetic field at different orientations and verify the dipole approximation. The Biot-Savart law is shown over here, where B is the magnetic field vector, U sub O is permeability of free space, U is magnetic dipole moment, R hat is the unit vector from the dipole to the observation point, and R is the distance from the dipole to the observation point. In the magnetic field of a bar magnet formula, B sub bar is the magnitude of the magnetic field at distance r, K is the proportionality constant depending on magnet strength and configuration, R is the distance from the bar magnet, and N is the power law exponent. The materials used in the observed model were the bar magnet, smartphone, meter, stick, Excel spreadsheet, and we were able to use apps like PHYS or Teslameter to record XYZ components. And we aligned the smartphone so to isolate Earth's field from the magnet's field, and placed bar magnet along the east-west axis to make its field orthogonal to Earth's. And the assumption we made was that the bar magnet can be treated as a magnetic dipole, and there aren't any other magnetic fields. The observed values were shown here. Use of mag, as shown before, is 3.3614. The experimental magnetic field was 4.02352. The power law fit was negative 3.0963. LNK was negative 14.335. And the observation distance, R, was 0.2805 meters. This was the first part of the computational model, which just showed constants and forces and just the definition of the dipole B. And you can see how the formula for B was changed in accordance with how we want to calculate B. This was other values where I also included some constants and to showcase how the arrows should be formed later on. Over here is the final computational model. The different arrows show the different forces on the magnet, and the following values over here were calculated, where B at a 45-degree angle at distance D was 1.45292 times 10 to the negative 6, 4.35876 times 10 to the negative 6, and the magnitude of B at 45-degree at distance D was 4.59 times 10 to the negative 6. The uncertainties were that the magnetic moment was estimated, not directly measured. The nearby electronics or magnets may have introduced background magnetic fields. The phone's magnetometer may have limited precision or calibration errors. Small misplacements in angles or distance can lead to large changes in a magnetic measured field, and the model treats the magnet as a perfect dipole, which may not measure the real bar magnet. Now answering the other questions. What if we had not compensated for magnetic north and aligned the setup at some other angle? If the setup had not been properly aligned to compensate for magnetic north, and instead the meter stick was placed at an arbitrary angle with respect to Earth's magnetic field, the background magnetic field from the Earth could have interfered with the measured magnetic field of a bar magnet. The magnetometer in the phone measures the net magnetic field, which includes contributions from both the bar magnet and Earth's magnetic field. By aligning the magnetic north, we ensured that the Earth's field remained constant and minimally disrupted the symmetry of our setup. If this alignment was not done, the Earth's magnetic field could have been added a directional bias or skewed the measurements at different points along the axis in perpendicular directions. This would have made it harder to distinguish the true contribution of the magnetic field alone. This result would be non-symmetric data, irregular magnetic drops with distance, or incorrect modeling when comparing with theoretical predictions. Therefore, compensating for magnetic north is essential to reduce confounding variables and isolate the magnetic effect of the bar magnet. And what if we had used two identical bar magnets stuck end to end instead of one? If these two identical bar magnets were attached end to end and used in the experiment instead of one, the total magnetic field of the combined system would approximately double, assuming they were aligned with matching poles. Since the magnetic field from the dipole is directly proportional to the magnetic moment, we would expect all magnetic field readings at a given distance to be stronger, specifically about twice as strong in magnitude in ideal conditions. However, the assumption only holds if the combined magnet behaves like a single. Extended dipole and the magnets are perfectly aligned without any gap or opposing orientation. In practice, the extended length of the double magnet could lead to deviations from the point dipole approximation used in our computational model. Especially at close distances, the field pattern would begin to resemble that of a finite solenoid rather than a point dipole, and the 1 over r cubed dependence might not hold as well. Additionally, because the source is now physically larger, edge effects and field line curvation may change how the magnetometer picks up the field, especially off-axis. Overall, we would observe stronger field values, but potentially more deviation from the ideal model, unless distance is increased to maintain the dipole assumption.